When guiding students starting their geometry course at an international school, I often witness their struggles with the process of proof. Since they are encountering the concept of proof for the first time, many students tend to shut their ears when I explain that reasoning involves both inductive reasoning and deductive reasoning, and the process goes like this: blah blah blah. Due to the unfamiliarity of the terminology itself, some students completely dismiss it, thinking, "I'm not interested in this, I just need to solve math problems." Occasionally, even if they manage to grasp and move on from the initial explanation, they stumble once again when faced with foolproof problems that come up soon after. Let's explain inductive and deductive reasoning using the example of Socrates. Inductive reasoning. Observation: Socrates is wise. Observation: Plato is wise. Conclusion: all philosophers are wise. In this case, by observing Socrates and Plato and finding the common attribute of being wise, we draw the general conclusion that all philosophers are wise. This is an example of inductive reasoning, where we derive a general rule from specific cases. Deductive reasoning. Premise: all philosophers pursue knowledge. General principle, premise: Socrates is a philosopher. Conclusion: Socrates pursues knowledge. Specific case. In this case, based on the general principle or premise that all philosophers pursue knowledge, we derive the conclusion that Socrates pursues knowledge. Deductive reasoning involves using given premises and logical rules to infer conclusions for specific cases. Through the example of Socrates, we can see that inductive reasoning derives general rules or patterns from individual cases, while deductive reasoning derives conclusions for specific cases based on general principles or premises. In reality, when children learn the concept of numbers and addition during their early childhood, they learn the fact that 1 + 1 = 2 by placing beads one by one. This process involves learning abstract concepts of numbers, quantity, and addition through empirical cases, but after a certain period of time, they come to understand that 1000 + 1000 = 2000 without counting all the beads, reaching a stage where they go beyond experience and engage in rational reasoning. This is the realm of rational reasoning that goes beyond mere experience. Most of human knowledge is built through inductive reasoning, relying on experience and observation, just like young students learn abstract concepts of numbers and addition through the experience and observation of counting beads. Afterward, as their ability for rational reasoning improves, they can deduce conclusions without counting all the beads, using given premises and logical rules. I've been asked this question many times by parents. Why is it normal to study Algebra 1 and then Algebra 2 in continuation, but geometry comes in the middle seemingly out of place? My response is: in the American curriculum, geometry is typically introduced in 9th grade, which marks the beginning of high school courses. Through the geometry course, our students directly and indirectly experience rational reasoning, and their perspectives are elevated through various problems and different forms of proofs. I believe that this approach allows them to develop a broader understanding that encompasses the entire abstract domain of algebra that follows, such as Algebra 2, Pre-calculus, and Calculus.